Okay, since your Rehan has doubt on the previous part, so I will start from there. Okay, I should share my screen first. Okay, so can you see the screen?
Yes, sir.
Okay, so it says that. So suppose there is a surjective function f from natural number to x. If there is a surjective function, so the statement was either x equal to empty or there is surjective function this. Now that imply x is countable, right? So that is what is the definition of countable? So either x is finite or there is a bijective function f from natural number to x. Okay, so this you are asking for this part, right? Okay, fine. Now first of all, see, 2 implies 1. So you already have seen the solution. So if you have any problem, you should ask here, okay? Because the solution is with you now. So if x equal to empty, first of all, so then there is nothing to prove, right? Then x is countable. Okay. So we assume the second part, that is, so now suppose x is non-empty and there is a surjective function f into x. Okay. Now also we have two cases actually. So either x is finite or x is infinite. So if, okay, so anyway, so both cases are we can tackle together. If x is finite, then again there is nothing to prove, then x will be countable. But anyway, we will go to we will do these two cases together. Okay. Now first of all, note that what do you mean by a surjective function? So that's mean for each x, okay, if inverse this one, this set is not empty, is a non-empty subset of n. Okay. Now since this is a non-empty subset of n, so we can use the well ordering principle of n. That's mean every non-empty subset of n has a least element. Okay. Now by using that we will define a new map G. Now define G x to n. Okay, so see it is given that f is a function from n to x. Okay, now we'll define a map x to n. So how we will define a map? So first we take one element x, right? That's mean from here. From here we will choose x. Now what is f inverse x? Now f inverse x may not be a single element, right? It can be a collection of elements. So what we will do, we will take the least element from there. That's mean we will first choose x and then we will take this set f inverse x. Now take the least element of that, that will be a natural number and we will call this one. Okay, so in that way we will define the map G. So therefore we define G such that G of X equal to minimum of all of these natural number such that f of n equal to x. Or in other words, we are taking minimum of the set f inverse x. Is that clear? Rehan? Fine, right? Now we will show that this map G is injective. Now this is very easy to see that is injective. Why? What do you mean by injective? Means g of x1, if g of x1 equal to g of x2, then you have to show that x1 equal to x2. Now if g of x1 equal to g of x2, say this is equal to m. So what does it mean? That's mean minimum of this natural number n such that f of n equal to x1, that is m. Also minimum of all this number n such that f of n equal to x2, that is also m. That's when m belongs to this set, again m belongs to this set. So this will imply actually f of m equal to x1 and this will imply f of m equal to x2. Since f is a function and x1 and x2 image of m, so that imply x1 equal to x2. So therefore G is injective. Okay, fine.
Yes, sir.
Now what we have this situation x to n. Okay, we have this situation. Now this is the map G and this is injective. Okay, now what we will do, we will take J new, we will define a new map G bar such that x going to gx, that is subset of n, and define as G bar of x equal to just gx. So actually this is the same map G, we are just restricting the codomain. Okay, or we are just restricting the codomain as the range of that function. So therefore this is bijective. So then the G bar x to gx is bijective. Okay, see now we have again two cases. So we could have splitted this case previously as well, but we can do that, we can split here as well. So now case one. So gx is finite. Okay, now if gx is finite, then x is also finite because you have a bijection between x and gx, right? Now that implies x is countable. So we are done. Now take the second case, case 2. Okay, so gx is infinite. So that's mean gx is an infinite subset of n, right? And in the last lecture we have proved that if you have a set, you have a subset of natural number which is also infinite, then you have a bijection from natural number to that set, right? If you remember that one. So there also we use the that what it is name, that Wheel ordering principle of n. Okay, so that's when we proved that every infinite subset of n is countably infinite. So that's mean if you take a infinite subset of natural number n, then you have a bijection from n to x. Okay, so by inductively we have defined that. Okay, so let H n to Gx be a bijection.
Sir, I cannot listen this line. And to GX means since GX is also a natural GX since we defined earlier GX to N.
Huh.
GX is also the output of GX is also natural number. So what is this the meaning of this line? This and to GX. I can't understand it.
See, I did not get your question. What are you saying?
What what is the meaning of this N to GX? And GX is also belongs to N. And what is the meaning of writing this H N to GX?
That's mean H is a function. This is a set. This is a set. H is a function from n to Gx, and this is a bijection.
Okay.
Okay, so this is a function from n to Gx. So this way you have write a function, right? Say function a from a to b. So this is a standard notation.
Hello.
Yes, yeah.
Sir, here it's not important that every element in every natural number is mapped to GX.
It is not important, or what do
Is
you
it
say?
not necessary? It is not necessary that every natural number is mapped to GX
Why?
because we have taken minimum of that the set natural number.
Right, but we have taken a new function, right? H. So that's when you can get a bijection from n to Gx.
Okay, sir.
Okay, and we have done this. We have done in the previous lecture that if Gx is an infinite subset of n, then there exists a bijection. Remember that there exists. Okay, so there exists a bijection from n to Gx, and we have taken that bijection. Okay, please go through the lecture notes very carefully and listen the lectures if you have doubt. Also, these lectures are available in the YouTube, maybe little bit differently, or maybe I explain little bit better there. If you want, if you don't get from here, you can listen from there as well. So I sent you the link. So this is most important. You have to understand, otherwise you cannot solve the problem. And another problem is that I have most of this problem I have done by myself only. So I have not taken from any book. So that is the reason I don't know in which book you will find this content, because these are so this content is in your syllabus. I have seen that you have countability of set, cardinality of sets, and I have done this by myself only. And I have taken some sometimes I have taken help from the internet as well for the questions or maybe for some proofs. But it is not from a particular books or particular notes or somewhere. So, so that is why it is very difficult to give a proper reference. So you should very carefully go through the lecture notes, listen the lectures. If you feel that okay, still this is not sufficient, I send you the YouTube link. You can listen from there as well. But you have to learn that. So there should not be any confusion. Okay, fine. Now we have a situation this H. So we have a situation N to Gx. Okay, so this is a bijection. Okay, again we have proved G bar X to Gx. Now this is G bar X to Gx. This is also bijection. So this is also bijection. This is also bijection. Okay. Now what is our aim? Our aim is to prove that X is countable. And what is the definition of that? So that's mean there is a bijection since X is infinite. So there is a bijection from natural number to X. Now how to get that bijection? So we can compose with H with G inverse. So in that direction. So now H. So this is my H and this is my G bar inverse X. So we get a bijection from N to X and this bijection is this one. Okay. Now since this compose H, N to X is a bijection, X is countably infinite. So that is countable. So we are done. So is that fine now, Rehan?
Yes, sir.
Okay, nice. Right. So now we show what is the importance of this theorem. So we learned something good. So previously, to show that a set is countable, you needed to show that either it is finite or there is a bijection from N to X. So you needed that, right? But as I told you, it is always difficult to find a bijection. But now this theorem says that you do not need to find bijection. It is sufficient to find a surjective function. And also you don't have to split the case finite or infinite. So that's mean it is sufficient to find a surjective function from natural number to X. So if you can find a surjective function from natural number to X, then you can say that X is countable. Okay. So that's mean we are just relaxing the required criteria. And this is equivalent to saying that this corollary so a non-empty set is countable if and only if the elements of X can be written as an infinite sequence. And remember that when we are saying that infinite sequence, the terms can be repeated. Okay, for an example, suppose your set is say 1, 2, 3. Okay, so why? But this is countable. But I told you here it is given that uh, a set is countable, non-empty set is countable if and only if the elements can be written as an infinite sequence. So, but this is a finite sequence, right? How you can express it, express this as an infinite sequence? You just can write 1, 2, and then all the repeated term 3, 3, 3, 3, 3. So this is an infinite sequence. So as I told you, the terms can be repeated. Okay. So that's mean suppose you are asked to show that a set X is countable, then you just make a list. If you can list all the element X in terms of infinite sequence, then you are done. So anyway, so I will give a short proof of this one, though it is very trivial corollary, but still I can give a proof for that. So first of all, since X is countable, so there exists a surjective function f natural number to X. Remember that here X is empty, it is given non-empty. So therefore we can get a surjective function. It does not matter, x can be finite, x can be infinite, both. That does not matter, but we always have a surjection from n to x, right? Now then we can write x equal to this set. So x1, x2, x3, x4. In this way we can list all the element where xn equal to just f of n for all n. So we are done, right? So if x is countable, that's mean we can list the elements of x in terms of a infinite sequence. Now conversely, yeah, any question? So if x is written as see, if there is no question, please mute yourself. Suppose x can be written as this one. Now can you tell me what is the surjection then? So can you give me the surjection from natural number to n, or how to show that x is countable? Yes.
लगा दे
Deepak Kumar, please mute yourself.
हाँ तो चार्ज का रुपया था क्या मतलब है लगा दे
Right. Okay. Now suppose x can be written as this one, this infinite sequence as a collection of infinite sequence. Then how to prove that x is countable? So that's mean it is sufficient to prove that there is a surjective function from natural number to x, right? Now can you give me the surjective function?
So we can map I to xi.
Right, we can just that this one. F of n equal to xn. Then obviously by the construction f is surjective. So therefore x is countable. Okay. So this corollary is very useful. This corollary is very useful. That's mean if you want to prove that a set is countable, you just make a list of x. That's mean you can just express x as an infinite sequence. Okay. Now we can see another theorem that is very simple. So finite union of countable sets is countable. Now can you give me a quick proof by using the corollary? Yes. You should give a proof of that one. That is very simple. You can take first of all 2, 1. Okay. So first of all, let x1, x2, x3 up to xn be countable sets. Okay. Now we will prove it is inductively. That's mean we first prove that x1 union x2 is countable. Okay. So we will prove that. Now remember that this is the case 1. So we have to split the case of empty one because that corollary says for the non-empty cases. So case 1 means if x1 or x2 is empty, then x1 union x2 is either x1 or x2 and hence countable. Right, so there is nothing to prove in that case. Now we assume that, so since this case is trivial, so assume both x1 and x2 are non-empty. Right? Now since they are countable, so we can make an infinite list. So let x equal to this set. So x11, x12, x13 in this way. X, say x1 this is, and say x2 equal to x21, x22, x23, this one. So these two, right? Since they are countable, so we can express x1 and x2. We can express x1 and x2 as an infinite sequence. Remember that the terms can be repeated. Okay, we are not saying that all the terms are different. So terms can be repeated. Some terms may be same. Okay. Now we express x1 union x2 as in this way. So x11, x21, x12, x22, x13, x23. In this way, we can make a new list. Right? That's mean we can list all the elements of x1 and x2. x1 union x2. So that imply x1 union x2 is count. And similarly, we can prove that x1 union x2 union x3 is countable. And after finite step, we can prove that x1 union x2 xn is countable. So any confusion here? If you can ask, so if you have any doubt. Okay, so there is another way to prove this is a list. For an example, say, so there is an alternate proof for this one. For an example, so given x1 and x2 are countable. Okay, so we assume that x1, x2 non-empty for this case only. Okay, so then there exist surjections, right? F1 into x1 and F2 into x2, right? Now we can define a new surjection if natural number to x1 union x2 such that f of 2n minus 1 equal to f1n and f of 2n equal to f2n. This is true for all n. And in this way we can prove that. So by the construction f is surjective function. So therefore, so since f is surjective, so therefore x1 union x2 is countable. Okay, so we can use the previous theorem as well, or we can use the previous corollary as well. Okay, so both way we can prove this part. Okay, so any doubt up to this? Yes,
Sir?
you should. Yes, yes.
The example of a non-countable set?
Your voice is very low. What?
Hello.
Ha.
Am I audible, sir?
Yes, yes, yeah.
So can you give the example of a non-countable set? Like, what are we going to show? So, like when we are making a sequence, infinite sequence, so that we can make from any set now because we are repeating elements.
Right. But how? Suppose you are taking the real number. How will you make express all the elements of real number as an infinite sequence?
So, like, I can take any element from that set, right? Like, if we have any real number in that particular set, I'll be
Right.
repeating.
But you cannot make a infinite sequence. So sequence is something different, right? So you cannot make a list. So you have to list all the elements in this way. What is the theorem? Yeah, infinite sequence means, yeah. So you can write that element in this way. That's mean x1, x2, x3, x4 in this way. So you cannot list real number in this way. We will
Okay,
prove
got
that.
it. Okay,
Huh?
sir. Got it, sir. Got it.
Okay. Anyway, we will prove that. We will prove that. So we'll have some examples and we will prove that. Now the next one is, so we have seen that any finite number of, so finite, if you take finite number of countable sets, if you take the union, then it is also countable. Now the theorem says, that is very interesting. If you take countable number of countable sets and if you take their union, then it is also countable. That's mean a countable union of countable sets is countable. Okay. So first of all, without loss of generality, assume. So okay. So first we take. So let xn be countable sets for all n. Okay, so this is a countable collection of countable sets. Okay, now without loss of generality, we can assume that each of xn is non-empty. Okay, why? Because if sum of xn is empty, then we can exclude them. Right? We can always exclude them. That does not matter. Okay. Now then, since each of xn is countable and non-empty, so therefore we can make a list. So that's mean x1 equal to x11, x12, x13, x14 in this way. x2 equal to x21, x22, x23, x24, x3 equal to x31, x32, x33, x34. So in this way we can make the list. Okay. Now can you tell me, can you give me the list how to count the elements of these unions? How to count?
So we can count diagonally.
Exactly. So that is the procedure. So we can count diagonally. That's when this is my first element and this is second, this is third. Now this is this. In this way you can count. So that's mean this will be my list x11. Then we will have x21, x22. Then we will have x31, x22, x13. So in this way we can count all the elements. Okay, so therefore we make a list. So that imply union of n equal to 1 to infinity xn is countable. Okay. Now similar concept works when you want to prove that the rational number is countable. Now there is a problem. So say this is a problem. Prove that Q, that is the set of rational number, is countable. Now can you give me a quick proof?
Uh, Natural numbers is the same as I cross A, right?
That, what?
Excluding natural rational numbers the same as I cross I minus 0.
I cross I minus 0. Yeah, but you need to prove that, right?
Yeah.
How you are saying that that is same?
So
You
it's
cannot say
written as
that.
P upon
Like
Q2 and we
any
can
natural number can be written of P by Q, right?
Right.
Hmm. And where P and Q are integers and Q not equal to 0. So P
But
belongs.
you cannot say same in the in because that
Oh
some
yeah, sorry.
rational number.
Yeah, okay, fine. Because okay, 1 and 2 are the same.
Right.
Hmm.
Because you have to prove that their cardinality actually same, but you need to prove that. You cannot say directly that their cardinality are same. So you need a proof for that one because it might happen that their cardinality are different because there are lots of element have the same and they this is a surjective function actually.
Oh, okay, sir. Then we can do it like this. You can first two
Anyway,
elements are
right.
0 by 1
Yeah,
and 1
your
by 1.
concept is fine. So we will do similar way, but there is a we will give it two different proof. Okay. So first of all, we can write q equal to q minus say q minus union say 0 union q plus three sets. Okay. So this is just a positive. This is negative. Okay. And we exclude the 0. Okay. So that is fine. So you can try with q directly, but I always prefer to split in that way. Okay. Now, how to list that element of q plus? You can write this q plus as in this way. See, 1, 2, sorry, 3, 4, 5, 6, then 2, oh sorry, 1, 2, 3, 4, 5, 6 in this way, then 2. Then 1, 2, 3, 4, 5, 6. Now this is 3. In this way. So right. So in this way, you can make the all the list q plus, right? And then you just this one now why this list is countable? Now you just count diagonally. Now remember that the terms can be repeated as I told you, right? Terms can be repeated. So therefore you can take an infinite sequence q plus as first component is 1, then 1 by 2, 2 by 1, then 1 by 3, 2 by 2, 3 by 1, then your 1 by 4, 2 by 3, 3 by 2, 4 by 1 in this way. You can list all the element of q plus. So terms can be repeated, okay? So terms can be repeated, right? So that implies q plus is countable. Now similarly, you can prove that q minus is countable. So therefore, q is a finite union of countable sets, so is countable. Did you get the problem?
Sir, what is the significance of this diagonal counting? Can you explain once again?
Significance means, see, you have a list, this one, but this is not a sequence, right? You have just a matrix kind of elements. Infinite matrix, infinite, that is infinity cross infinity kind of matrix. And you want to count the elements. So you need this matrix to an array, one single array. And by diagonally, we can make this infinite matrix to a single array. And we can count, we can list as an infinite sequence.
Okay, sir, got it.
Okay. So diagonally counting means actually you have an infinity cross infinity matrix, and we are listing those infinity, the elements of those matrix, infinity cross infinity, to a sequence. So that's all. Because our theorem says you can make a set is countable if and only the elements can be expressed as an infinite sequence. For an example, x1, x2, x3, x4 in that way. Okay. Now the next lemma is the Cartesian product of a finite number of countable sets is countable. So now let x1, x2 up to xn be countable sets. Okay. Now if xi is empty, then the product x1 cross x2 is also empty, right? So we are done. So assume xi is non-empty for all I equal to 1 to up to n. Right now, first we prove that. So first we prove x1 product x2 is countable. Okay, then we are done, right? Because if we can prove that x1 cross x2 is countable, then we can prove that x1 cross x2 cross x3 is also countable. In that way, we can do up to the finite step. We can do the we can prove that x1 cross x2 up to xn is countable. Now, what are the elements of this? Now let x equal to. Okay, so we first prove that. Better to write in that way, or shall I write in that way? It is fine. It is fine to write an x1, x2. Okay. Now let x1 equal to x11, x12, x13. This list. So x2 equal to x. There will be a problem, I think. Okay, it is better to write x, replace x and y. Otherwise, okay. We first prove that x cross y is countable where x and y are countable. Otherwise, we have some notational problem. Now let x, since x is countable, we can write x as x1, x2, x3, x4 in that way, right? And y equal to y1, y2, y3, y4 in that way. Right? Now then, what is x cross y? X cross y is that set. x1, y1, x1, y2, x1, y3, then x2, y1, x2, y2, x2, y3, then x3, y1, x3, y2, x3, y3, that, and infinite. So again, it is an infinite cross infinite matrix form. Again, we can count diagonally. Right? So therefore, the element of x cross y can be written as an infinite sequence where the terms is this one. So x1, y1, then x2, y1, x1, y2 in this way. So we are done. Is that fine that we are done? Yes.
Yes, sir.
Okay. So therefore we prove that if you have a finite number of countable sets and if you take that product, then it is countable. Now what about infinite number of product? For an example, if you have instead of finite elements, if you have infinite number of sets and if you take their product, will that be countable? What is your guess? Yes? Yeah, I need some answer. What is your guess? Can it be countable? You can guess, right? You don't have to give the answer. You have to just guess it.
No, not countable.
Okay, so is there any argument for your guess or you just guess it?
Just a guess.
Okay. In fact, you don't have to go that far. So tell me if you have 0, 1, this set cross 0, 1, cross 0, 1. You have this infinitely number of this. So that is what you can say 0, 1, that power natural number. Okay. Now can you tell me this set? So you have just two element set and you have that infinitely number of two elements set and then their product. Now is this set countable or uncountable? What is your guess now? So we are not taking only countable set, we are taking only two elements. That is the simplest one. And we are taking their product.
Wait, these are infinite amounts, right?
Yeah, infinite amount. So we
Then
have
uncountable.
dot, dot, dot. Now this set is uncountable. Okay. So you can say that in terms of cardinality, you can say that this is the smallest uncountable set by the construction. Okay. Because if you take only the single elements, then this will be a single element. Their product will be single element. We are just taking one more and we are taking their product and we get one uncountable set. Now how to prove this is uncountable? Okay. Now you have to remember, you have to find that a proof. So we will prove by contradiction. So prove by contradiction. We'll prove by contradiction. Okay. Now, if possible, X is countable. So what do you mean by X is countable? Then there exists a surjective function f from natural number to x. This is if and only if criteria, right? Now since x is countable, so we have a surjective function f from natural number to x, right? So therefore x can be written as x1 comma x2 comma x3, this, where xn is just f of n. Okay, and remember that these terms can be repeated because we are saying this is a surjective function. We are not saying that this is a bijective function. Since it is surjective, so terms can be repeated. Fine. Now can you tell me what is my x1?
Some random strings of 0 and 1.
Exactly. So x1 is itself a sequence of 0, 1. So x11, x12, x13, this. Similarly, x2 itself is a sequence. x21, x22, x23, this. So xn in similarly that will be xn1, xn2, xn3, where so xij is belongs to either 0 or 1. Okay, fine. Now the question is, see, if x is countable, then x can be written as this list and this is the list. Now how will we get the contradiction? Now we will prove that this list is not complete. Now can you construct one element which is different from this? That's mean, can you construct one sequence of 0, 1 which is not in this list?
So we can go like across the diagonal and revert each element.
Exactly. So we will go first in this direction. Sorry. And reverse the elements. So that's mean now take y equal to y1, y2, y3 in this way, where yn equal to 0 if xnn equal to 1, and this is 1 if xnn equal to 0. Okay, so that's when we are taking this type of elements and we are just reversing. That's mean if it is 0, then we are taking 1. If that is 1, then we are taking 0, right? So that imply y belongs to that set. Right? That's mean y is in x. Okay, but y is not equal to xn for all n, as the nth component of y and xn are different. Okay, so therefore the list is not complete. So thus the list is not complete, or you can say that f is not surjective, as y belongs to x, but there is no n in natural number such that f of n equal to y. So this is a contradiction.
What does the y represent? Yn and y1.
Yes, what is your question?
What does y1 represent?
Can you write? I could not hear.
What does this y1 represent?
Yn or y1.
Yes, yn means y1, y2, y3, all.
Okay. So what is y? We are taking y as an element of x, right? And what are the elements of x? This is a sequence of 0, 1. So y, okay, I should write, right? You are saying that one. So yi belongs to 0, 1. So y is an sequence of 0 and 1. So that's when we can take y equal to y1, y2, y3, where yi belongs to 0 and 1.
Means we are taking similar sequence y like x1, x2, and xn. We are taking similar like x1, x2, xn. Y is also similar to like x1, x2, xn.
I'm not getting. Are you saying something or?
Yes, sir. I am saying that is the y similar as like we are representing writing x1, x2, and xn. So we are writing y.
No, 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 no. Y1 is similar as x11 kind of thing.
What is this y? The whole y is. The whole y is like the x.
Y is an element of x. So y is kind of x1, x2, x3. Y is an element of x. Okay. So I got your confusion. You are saying that here you have x1, x2, x3, and here you have y1, y2, y3. So they are same kind of thing. So this is not. So y is the category of x1, x2, x3, and y1 is category of xij. Okay. Fine. So any other confusion, or do you want something so I can recall that? Fine. Okay. So in this way, we get one uncountable set, right? Now, similarly, in a similar fashion, we can prove that. If you take closed interval 0, 1 is uncountable. And as a corollary, you can prove that R is uncountable because 0, 1 is an infinite subset of R. And if R is countable, then as a subset of this, that will be countable. But since this is uncountable and R is and this is a subset of R, so from this you can say that R is uncountable. So as a corollary, you can say that. Okay. Now how to prove it? So this is uncountable. First of all, you just look at the decimal representation of 0, 1. Okay. Now tell me, what are the decimal representation of 0, 2? 0.2.
0, 2, 0, 0.
Right. So this is 1, 0, 2, 0, 0, 0, 0, 0. This one, right? And or it is the same as this, or you can write it is as 0.19 and then 999. Both are same. Right? You know, right? Both are same.
Yes, sir.
Right. So these two different kind of decimal representation. But since they are all are 0, we can cross it. So we can say that this is terminating decimal representation, and this is non-terminating decimal representation. Okay. Similarly, each element, similarly 1, you can write it is as 0.99999. Similarly, 0.127, you can write it is as 0.126999. Okay. So each terminating term you can express as a non-terminating term as well. So we will choose this only, and we will not take this. Okay, why? Because we want one unique decimal representation of this. Okay, and then we can write let x equal to 0 union all positive non-terminating decimal representation of the elements of this. Okay, so that's mean x equal to actually closed interval 0 1, and each element of x has a unique decimal representation. Right? Now, why we are doing that? Because we need that uniqueness, that is unique decimal representation, to get a contradiction. That's mean it is a complete list. We need that. Okay. Now, so now we will prove by contradiction if possible. If possible, let x be countable. Now then there exists a surjective function f from natural number to x. Okay, so that's this x can be written as x1,
Sir?
x2. Yeah.
So why we are taking a non-terminating decimal representation?
Right, because what we want one unique representation of x, of the elements of the 0 1, because you can see that if you look at all the terminating numbers, say 0 1, it has two representation, right? Say for an example, this one, this is 0.2 and 0.1999, each has two representation, exactly two. So
No, sir, but
therefore we are taking
0.199
only one.
but 0.199 is a different number, no?
Which one?
0.199.
No, both are same. That is a ninth standard actually knowledge. This one you should know. They are same. They are not different. That's why I'm writing now. Okay, it is terminating. I'm saying that it is not stopping, right?
Yes, sir.
This is
Okay.
infinite. Okay, this is not stopped here. It is going. Okay, that's mean 0.99999. It is going. It is non-terminating. That's why I am using the word, right? Non-terminating. So it will not terminate. It is going, and that will be equal to 1. Right? Now it is fine, right? Yeah, I should give the dot. Otherwise, anyone can misread that. Now it is fine, right? So they are same number. Yes.
Yes.
Okay. Thank you. Thank you. Thank you for the correction. Okay. So therefore, we can there is a surjective function from f n to x, and x can be written as this one. Okay. Where x n equal to just f of n for all n. Now again, we will give the contradiction that this list is not complete. Okay, so you are saying that there is a surjective function from n to x, right? So if x is countable, then there is a surjective function, but we will keep that, we will prove that there is one element from x which is not in that set, and we will use a similar concept. For an example, x1 equal to 0 point x11, x12, x13, x13, 14 in this way. x2 equal to 0 point x21, x22, x23, x24 going. x3 equal to 0 point x31, x32, x33, x34, and similarly xn equal to 0 point xn1, xn2, xn3. Okay, where xij belongs to that set 0, 1 up to 9. Okay, now we define again we define a new element. So now let y equal to 0 point y1, y2, y3 in this way. Okay. Uh, just a minute. So we will write in this way where yi belongs to that set 0, 1 up to 9. Okay, and the main property is we will take yn equal to 0 if xnn is not equal to 0. Okay, and we will take this is 1 if xnn equal to 0. Okay, so that's mean you can note that the nth term of this decimal representation of y is different from the nth term of the decimal representation of each of xn. So we actually again we are going diagonally, and here we are not reversing. We are not reversing that directly. We are just changing the number. That's when if this is 0, we are taking 1, and if this element is non-zero, any number that is 1 to up to 9, then we are taking 0. So then it is easy to see that y belongs to this set 0, 1. Okay, so y is in this set. And also you can check that y cannot be a terminating set because we are not taking 999, right? So you better to say that you can say that y belongs to x as well. Okay, and yn is not equal to xnn for all n. So that imply y not equal to xn for all n. Okay, so thus there does not exist any n in natural number such that f of n equal to y. So thus f cannot be surjective. Okay, so we are done. So therefore we assume that 0, 1 is countable, so that is false. So 0, 1 is uncountable. And as a corollary, you can say that R is also uncountable. Okay, fine. Now there are many applications of this one as well. For an example, do you know algebraic number? Have you heard
Excuse me?
about it?
Uh, like
Huh,
they are solutions of polynomials with this thing, uh, integer coefficients.
exactly. So algebraic number, it is a real number is called algebraic if it is a root of the polynomial a0 plus a1x plus a2x square plus an xn for some n and ai belongs to z. Okay, so this is called algebraic number, and similarly you can define that transcendental number. So a real number is said to be transcendental if it is not algebraic. Okay, so that's mean if you have a real number, so that number either that will be algebraic or transcendental, one of them, right? Now this is your exercise. Prove that the set of all algebraic number is countable. In other words, you can say that it's a similar way. You can say that, prove that the set of all transcendental number is uncountable.
Sir, do algebraic numbers include complex numbers?
No, no, no. It is a real number, right? We are saying that all a real number is called algebraic.
Yes, sir. Yes, sir. But like, okay, but so
No, no, no. In
so
the definition,
imaginary
a
unit will
definition
not
I am
consider
saying
it
that,
as an algebraic number.
right? Because here we are saying that a real number is called algebraic. Okay. So in other words, okay, there is algebraic real number. Or in other words, you can say that real number, this set is union of that algebraic number union with transcendental number. Okay, so by the definition we are saying that a real number is algebraic, right, if it is a root of the polynomial this where the coefficient coming from the integer. So that's mean algebraic number must be a real number, and a real number either algebraic number or transcendental number. So if you prove that the set of all algebraic number is countable, then automatically you are proving that the set of all transcendental number is uncountable. Okay, so I am not going to prove it here. So you have to prove it by yourself. This is an exercise for you. So now that countability part is done, so you should do by yourself. So anyway, all of these problems are available in that link, that YouTube link where I sent you. If you don't get, then you can see from that that YouTube from my YouTube link. Otherwise, you can find this kind of solution in from internet as well. If you search Google that prove that algebraic number is countable, then you will find a proof. But I suggest you don't go for the Google search and don't read from my YouTube link as well. Try by yourself. So if you can solve by yourself, then only you can solve this problem, this type of problem during exam. Because here I solve few problems, right? A few theorems. That theorems will not be there in exam. Okay, in exam you will have some problems, this kind of problem. This kind of problem. For an example, we can ask this one. Prove that the set of all algebraic number is countable. We can ask this kind of problem. So you have to do this kind of problem by yourself. Okay. Okay, I can stop sharing. And actually few students asked that, okay, what is the reference book for this part, that is countability. So frankly, as I told you that I have not follow any book, because most of the proof where I send you that note, so I did by yourself, I did by myself only. But that does not mean that that will not be searchable or that is not available in any book. If you search Google that countability of sets, then you will get many types of notes. Even you can get this part from a book. So you can read from any book. So I cannot suggest one particular book because I did not follow any book. So as I told you, so I most of the proof I did by myself only, and I have taken the content from the internet as well. And some proof also from I have taken from the internet as well. Okay, so don't worry about that. You can stick with the class notes, you can stick with the class lectures, and for the problems, you can follow that assignment problems, and you just search the similar problems from the internet, or you can follow a book. So if there is a book where you can find the cardinality of sets or that countability or countable or uncountable sets, you can read from there as well. There are many books where you can find that. So yeah, so if you find any analysis book, that real analysis book, then you will find that countable and uncountable path will be there definitely.